one. Sorry, just a second. All right, my name is Quentin Champer.
My name is Yana Kinchana.
And we're presenting today for the University of Illinois. So just to start off with, this is a quick image of the final product of our design, but we're going to walk you through how it all gets started.
We began our design with a few preliminary design criteria. The first was to maximize the floor area on the upper levels, and from this led to a design which we could create variable floor areas as the levels increased. We wanted to maximize the net income in the upper levels. The second was to increase redundancy in the lateral systems, so if one of the components failed, the other components could take on lateral loads. And finally, we wanted to prioritize stiffness because the drift costs bore the highest economic weight, so we wanted to create a more rigid structure.
So these preliminary considerations led to this floor plan that we started out with. And some things to note are first that these 4 dark boxes represent sort of a modular system where each box contains 2 sets of lateral resisting systems that resist loading in perpendicular directions. So the dashed lines indicate where the lateral bracing is. Also, you can see the lighter lines on the diagonal represent 2 possible exteriors of the building, so you can see that there are 2 separate floor areas that we can vary with height. So this is just a sort of a close-up of our modular system. You can see that there are large cross bracing in one direction, and it's kind of hard to see, but there are 2 sets of smaller worn trusses in the other direction. Also, you can notice that in this picture, there's 2 sets of 2 worn trusses, but that gets changed later on. So the biggest challenge we had with design was the weight criteria. This is actually our team members' first time at this competition, so we weren't quite sure how to estimate the weight. So we worked through the densities of balsa and pine plywood to come up with a weight projection, but this was way below what the actual weight of the building was. We underestimated by about 1 pound. So we had to cut a lot of weight, and one way we did this was we took that double worn truss and made it a single worn truss, which resulted, we lost some stiffness to the building, but we increased our acceleration performance, so there's a bit of a trade-off there. Another solution was we removed the 3 upper floors of the building, but fortunately the adaptability of our floor area offset the economic impact of this. Our other main design challenge was that the modular system depends heavily on the modules being able to talk to each other and effectively transmit lateral loads. So initially we had sort of an in-plane bracing system, but the weight consideration made that infeasible once we started constructing it, so we switched to a moment connection design.
This is a picture of our original core before we gutted it to improve the overall weight of the structure. We had 2 tests to test for the material properties of the members. The first was a simple single-point bending test, which was used on quarter by eighth and quarter by quarter sections. And we used the relationship between the moment of inertia, and the Young's modulus and the displacement to determine the modulus of elasticity, which was around 480 kSi. And we also wanted to test for the rotational stiffness of the connections by applying a moment and using the relationship between that and the angular rotation to determine the rotational stiffness.
Okay, so we used SAT 2000 to model our structure, and we started off by just modeling a few different geometries and seeing how they performed. And then we took the output and wound up with our actual design. So right here you can see there's just a table that sort of summarizes our maximum relative drift and absolute acceleration for the 3 ground motions. And you can see that we did achieve our stiffness goal. Our building is fairly stiff. We wind up with some pretty small drift ratios. Our analysis has 3 large limitations. The first is that we didn't include nonlinear effects and inelasticities. So for instance, strength loss due to crushing of the wood, permanent inelastic deformation due to crushing of the wood. As connections rotate, they start to fail and they lose a little bit of strength, lose a little bit of stiffness. These were not included in our model. Also, our material was highly variable. We had a range of 280 to 725 KSI in our tests, but we just modeled all of the wood as 480 KSI. Finally, we modeled all of the connections having that rotational stiffness of 64 pound-inches per radian. In fact, there are different geometries present than the one we tested in our structure at certain locations, and the actual stiffness of the joints is going to depend on exactly how each of the joints were constructed, how well we were able to clamp the joints, whether or not glue made full contact, etc. So those are some limits of our analysis. And that concludes our presentation. Do we have any questions?
Any questions from the judges?
Since you didn't analyze the final configuration, how did you determine the drift and acceleration levels?
Oh, I'm sorry. Maybe I didn't make that clear. Yeah, we did analyze with our SAMP analysis.
Yeah, I thought you said you weren't able to analyze. You weren't able to analyze the final joint configurations.
Oh no, I'm just saying that with the joints, we just simplified it and said that all the joints were uniform. So we modeled all the joints as the same. But our final geometrical configuration we tested in SAP. We just made some simplifications with how we modeled the joints.
You mentioned at the beginning that a key goal was maximizing floor area at the upper levels. Can you talk a little bit more about how that configuration with the 4 pods and the location of the brace on the inside edge actually achieves that?
So we'll go back to our, well, basically, so these sort of lighter diagonals, like the way that the 4 things are situated, we can change whether or not they're connected to the inside or the outside face. So you can see when they're connected to the inside corners of our 4 modules, we have a smaller area. And when they're connected to the outside, we have a larger area. So at the top of the structure, we use that larger floor layout, and at the bottom half, we use the smaller one.
Audience?
Do you have any estimate of the period of your structure?
No, we don't.
Thank you.